So today we will be discussing the AtCoder contest. Uh, it was yesterday's AtCoder Beginner contest ABC 463. Right, so we'll be discussing few questions in here. Let's start with the first question. So what does it say? The first question. It says that we have got two variables xy and we have to report if these are in the ratio 16:9. Right. So to check if these are in the ratio, what we see, we just see that x by y is equal to 16 by 9, right? In what do you say, general programming, we cannot check by this direct fraction if it's equal or not. So we can check it instead. Is 9x equal to 16y? By the way, we have been given that y is greater than 1. But if we check like this, it means terminates any runtime error also if there are. So right, so this is the way we check. So we can just check directly 9x is equal to 16y. And if correct, then this is our answer. Else we print false, right? So the code is very basic for this one. You can see if it's this ratio is same, if the ratio is same, then we see out yes or else no, or else we could have just printed the boolean value of this directly. So right, the two-line code. Let's move on to the second problem. What does the second problem say? That we are given n strings, right? N strings, s1, s2, like this, sn. Each string is of length. Each string is of length 5, where s of 0 represents Ath row, s of 1 represents Bth row, sorry, column, Ath column, Bth column, like this, and s of 4 represents Bth column. We need to find that if there is a vacant seat in the given means the column we are given, right? So what do we need to see? Look, we are given a value integer of x and n. So n we already know is the number of, and x is the row in which we have to find. So x is a character which can be a, b, c, d, a, b, c, d, e. So there are 5. Okay. So for each string, we can see the example here and easily look at the example that this XXO is 8th column. OXX is the bth column, this one and this one, and this one is the bth column, like this. Then this is the third column, and this is the fourth, and this is the fifth. Right. So we are given 3 here. We are given 3 here, and we need to check that A in the 8th column, that is XXO, this one, if there is a O. So yes, there is a O, so we print yes. And similarly for 5 comma C, that we have given 5 strings, and in the Cth column, that is the third column, there if there is an O, there is only X. So it's first X, second X, third X, fourth X, fifth X, all of them are X. We print no. Right? If there would have been a O, we would have printed a yes. So what do we do first? We take in our X, and if it is A, we make an integer index 0. If it's E, we make an integer index 4. So how can we do this? We can simply do the indexing by value of x, as x is a character, is x minus ASCII value of a. So for you can check for a it gives a means 0, and for e it gives 4. So all of them a b c d e will correctly map to 0, 1, 2, 3, and 4. Now for all the n strings we only need to check if the index value of the string, if one of them is O, turn our answer as true, or else it's just false, right? So what do we do to check this? For all string input, we take in the inputs, right? And then for that particular index, you can look at the answer here. That is, we have taken n strings, a vector of n strings, okay? And also we have made k as our index. That is the character input. This you can see as x. This is the x, right? And then we are just checking this index. K is the index. Okay. So then what do we do? We make a flag value false, and we check. First, we take up the input of the strings, and then we check if the ith string, ith strings I runs in from 0 to n, and ith string's kth value, that is index value, is equal to 0, means O, then we make the flag true and we break. If the flag is, what do we say, it's true, then it's yes, or else it's no. It's a very simple code. You can see and check the output too. So it runs normally, right? So yes, this is also a very simple code. So let's moving on to our third question. What does the third question say? Like, let me first explain the question, right? Okay, then we'll discuss it. So there are n Takashi in a conference room. So let's consider n people in a room, right? And at time L, a person of height h moves out of the room. So this is a room, and there are many LI HI pairs. And at LI time, someone moves out of the room of height HI. So the number of people in the room decrease by n minus 1 or whatever it is. So the number of people are decreasing in the room, simply we can say. And then what happens? We need to return for Q queries. For Q queries, we need to return that if means this is how the time is going. At this point, there are all people in the room. So the max height in the room will be the height of all people, right? Maximum amongst the all. And here all except one have left at this point. So maximum will be the remaining one's height. For Q queries, we have been given that we need to tell at time this t means just greater than t, that where a value of the maximum height is. Like the number of people are decreasing here and there. Means after we go this way. So we need to just check that what is the maximum height at this point, right? So how can we do it? So there are few ways. Simply, first of all, we can easily see that we need to have an array which contains the maximum of heights, array of maximum heights along the time. So what can we do? Instead of going this, that decreasing the maximum height from this to this, we can loop the array in this way, that we go from this maximum here till the maximum currently present here amongst all. This is a simple this is a simple concept of suffix maximum suffix array. So you see, we will take an example. So first we have been given n. N is this value, and then we have given n pairs of height and time. That is h1 and l1. So this is the height and this is the length in time. And then there are q queries of t. So right. So we have been given 31, 4, then 26, 5, then 3, 5, and 15, 9. So what happens? Let's check the example. Look, so first of all, what we have is at times like this, from 0 till, let's consider 9 here, as 9 is the last time a person leaves. So what is the maximum at this point? Till 4, that is when the first person leaves, the maximum is 31, right? After that, it's till 5. At 5, 26, and third height person 3, right? So till this, the maximum is 26. And from 5 to 9, the maximum is now 15. So you see, it's a decreasing array, or simply what we can say that it's a suffix max array, or this value is the maximum till here, this is the maximum till here, and this is the maximum till here, right? So what do we do? Instead of going one by one, we store in a suffix max array the maximum height till that number of people have left, or till IA, right? So what do? We simply define a suffix array where n is the maximum at that point, or that is equal to the only person remaining, that is v of n minus 1. Then in n minus 2 to 0 we go on this way, and we just check. If we update the value of the suffix max by max of that current element or our max value, right? So this is what we do simply. Then after storing the values in the array, so look what we have got. What we had got in our value was 31, then 26, then again it was at 5 it was again 15, right? So like this we had got our values, and the value we had here was 4, 5, and 9. So we have been given the values to search in from was 3, 4, 5, 6. So we have, it has been mentioned here that from the time ti plus half minutes from now we need to check. So the value from 3.5 minutes is closest is the value force, which is already 31, right? So the closest value till 4 is 31. Similarly, for 4, the closest value is 5, which is 26. Now for 5, this it will be 5.5. For 5.5, the upper bound is at 6, or the closest what we can say is 9. So till 9, the height maximum is at 15. Right. So this is a simple upper bound case. And for again 6, the upper bound is 9. So it's just 15. So we go on like this way. So how can we code it? We have already seen how we do the suffix maximum. Just to find the value at that point, we need to have that L of I, that vector we were having of the length of time, right? And for this case, we need to find the upper bound in L of time t. Whatever index this returns, this index it returns, this is our value in the suffix array we need to print. We can see from the previous example. From the previous example, we look. We see whatever will be the what do we see, upper bound of this value in L. This is the L, and whatever will be the time t's upper bound, that is 9 here. So the suffix value, suffix max, will be the value we need to print. So it's simply nothing but the index what we are given. We just print the suffix value at that index, right? So it's not much to understand. We print this index value. There's another way, like you can do it also in this way, or you can just have a pair of vector elements. You just take in the pair. This contains time first, that is Li, and then there is max Hi till that Li, till Li, right? We can do this max while taking the input. So what I mean is, when we are taking the input, we see that it's 4, Li is entered, then it's 5, then it's 5, then it's 9, right? So we have maximum till here as 31, then maximum till here as, means it will be going in the opposite direction, we all know. Right? So it will be 15, then 26, then 26, and then 31. So we have stored this in a map vector, right? So this is what we have stored. So instead of now doing the upper bound on that Li list, we do a whole upper bound on this whole suffix max list containing the time. So how do we upper bound it? You just check the upper bound of the time with a long max. Or else we could have done a lower bound with the same value too, but our upper bound is much preferred. So we do this and we get our current index at IT. And so we know at IT's second value is our answer. So it's not much. Again, it's the same concept, just made in a shorter way. You can check out the code here. I have written the both of the ways you can solve the problem. So this was the more short form way, and this is the way I did during the contest. So I wasn't able to think of the shorter way. I was going in that direction, but it took me some time. So I just wrote the normal code. So it's V and then L. We first take in the V values, that is H values, and then the L values, that is length of time, whatever it is. And then SF is the suffix max. Suffix max contains the value going in the opposite direction. If the maximum array, then we take in Q queries. And as we know, what we do upper bound in L of T, we do here L dot begin to get the index of upper bound, so that we can do it from, we can retrieve the value from suffix max array. Instead of this, we could have also done this one. You can check the code out here, right? So we first take in L, then we take in a vector of pair, which is v of length n again. So first, for the second value, we take in the heights, and the first value we take in the time, right? Then we do a maximum array, which goes on in this way: suffix max at top, whatever the maximum will be, or else we'll update it to the new max, right? And then for Q queries, we do an upper bound, and we check the pair P and L long max. Why do we do this long max? See, for a case here, if 3 and 5, this is the height and this is the time, right? But we have reversed it here, so it's 5 3, and think if 5 4 are there. So if we do a upper bound and just keep these values, then it will give a upper bound at this. But we want to check, go over this 5. We want to go over this 5, right? That's why, for what can be the last maximum value possible here? If we have only people leaving at the fifth minute. So what we can have here, it goes until 5, 5 long max. So this is the value we can go here, but we need to skip to 6. We need to check its upper bound. That's why this is the maximum value at 5 which can be attained. So T and long max is the upper bound on which we are making it. Right. Let's move on to the last discussion, last problem discussion. So it will be D, maximize the gap. Right. So it's a standard. I will read out the question for you, then you will get to know that it's a standard binary search problem. First, let's see how it is a binary search problem. So there are enclosed on a numbered line, right? There again enclosed on a numbered line, which is from Li to Ri, right? So Li to Ri, and we have such means n clothes. We need to select k clothes amongst them so that the distance between two clothes, the maximum distance between two clothes, minimum maximum possible score when choosing k clothes of them overlaps. So we need to find the maximum possible score, but the score is defined as the minimum distance among all clothes. So the cloth L and R1 means L1 and R1 and L2 and R2, these have a score of R1 minus L2's mod, right? So whatever the distance between the cloth is, think of the cloth as like this. Here is a cloth, again here is a cloth, then this is the cloth. So the distance between them is what? It's something like, let's consider x and it is y. So let's say that y is greater than x, but we see that we only take the value x, right? X is the minimum amongst them and y is the maximum. So score is x, but we need to maximize this x, right? So we need to kind of equally distribute it all amongst them. Whenever we see questions like maximum of minimum or minimum of maximum, it clearly hints us at some binary search and answer type of thing. So in general, when we say that select k from m, instead of this, we can have this, that can I select k? We don't have to select k. I am checking can we select k and get some value k less than n, means some number of clothes, means c, which is less than n, I mean k, and then we get our value, means the count, as the minimum or maximum, whatever it is. So how do we check the minimum and maximum? First, let me tell you how can we check the what do we call that? The cloth length. This is the cloth length, and we need to see the maximum gap formed between them. Right. So in general, looking at the values we see to maximize this, we need to check if from this cloth length at distance d, can we have some cloth at distance d? If yes, what we can, if we can have a cloth, it's a yes or it's a true. And if no, then it's simply a false. So how to check the maximum number of clothes that can be formed? This is a simple interval scheduling problems, similar scenario, right? So when we see things like this, that the cloth length is static from here to here, then we have a cloth from this to this, then there's a cloth covering this. So we usually sort, we have been given the L and the R. So we usually sort on the basis of the last value so that we can count maximum from the start. So it's like, how do we go from here to here? First, we sort this R, the first one, that is, let's consider 3 comma 5 as mentioned. Let's take an example for ourselves. It's 1 comma 100. We have a cloth at length 1 comma 100. Then we have at 2 comma 5 and at 6 comma 9. So if we sort the clothes out in this way, that the first one is at 1 comma 100, that is sort by the first value, and it will cover this length. And then at 2 comma 5, then it will cover this length. And then at 6 comma 9, so it will cover this length, right? So if we want to pick up the maximum number of clothes what we can get, the maximum number of clothes which we can get with a distance d between them, we cannot start from this end, right? Instead, what we can do, we can start from this end. If we have sorted on the basis of first value, we can start from this end counting the number of clothes, and then look, if we want to have the d as 1, then we check, for the first value there is one cloth which is one distance away from this length, right? So we get our count as 1, this, and then again we increase it to 2. So it's simply the count has increased to 2. But instead here, we see that beyond 1 to 100, there cannot lie a second cloth, as there is nothing greater than 100. So we always need to check that we go in this direction, the opposite direction, or else instead making it clear, we can simply do interval, means the schedule intervals, we can sort them on the basis of the last index. It will be the same thing. Actually, if we just look at it, it's just symmetric on both the sides. So what we had 100, 1 comma 100, 2 comma 5, and 6 comma 9. So instead of sorting on basis of this, we sort on the basis of this. What we get? 2 comma 5, 6 comma 9, and 1 comma 100. So these are the values what we get. Yes, it's simple. So now if we start counting from this direction, we can get the same count as it has a distance d between them. So again, we have got our count as 2, maximum count as 2, right? So this is simply the way we can count the number of maximum clothes which we can have at a distance d, the distance d. Here the d we have considered is 1. Now how do we see the effect of binary search in it? Now you see that we have made a function which tells us, can we have cloth C selected at distance d, at distance d between, them, right? at distance d between them. And if the c is greater than equal to k, what does that mean? That yes, out of k we can select k number of elements or greater than k, that such that the distance between them is d. So if we return this, it gets us a true or false. That is at d, we have got our answer. And if not, then we get our false. Let's see, isn't it true that if we can get at a distance, think of it, if we have got at a distance 3, if we have got at a distance d equal to 3, so we will get always at a distance d equal to 2. As we are decreasing the distance, it's not necessary we can't pick up the same clothes, right? So we can always get, if 3 is true, is at the fun if the function at 3 gives us true, then it will for sure at 2 give us also true. But it does not give us surety that at a distance 4 it gives us true, right? It may be true or false. That is, the maximum distance between them can be reduced. So what we do then, but we already know if there is a false, that is, if at 4 the distance won't be true, so we know at a 5 distance will always be false. So does not this look like a monotonic true then false, this type of a thing? It simply looks like the same thing we do for binary search and answer, right? So now what do? We now check for all the values. What we were doing, that function was taking in the mid value. Mid value was our value which we were checking the output on, that is the distance d. Then our length vector k v, and at last we were taking in the value, uh, yes, we were taking in k, that is if we can select k values from there, and there was a counter c going on, and it returns after doing the operation c greater than k. So this is what it returns simply, right? Now we check, and we can always get our answer for this d as true, true. We can always get at a distance less, but we don't know we can get at a distance greater. So it's like a basic monotonic function, and we can check for all the values of d between them. If we ever hit this sequence at the middle, we get our first true. This is the answer we have got, right? So in my binary search code, what I implement is, my implementation is usually I'm taking the last two remaining values out of here. So if it's true false, then we get this value. First we check this, or else we check this, and whatever the first value is, we return. So if it would have been, our bracket array would have been like true comma true, we could have checked for the highest true amongst them, that is the high value, and returned the place at this, right? So let's look how does the code look like. I have already mentioned two ways which we can get our predicate function. You know, the binary search and answer works basically on the predicate function, that is the function returning true or false. This function we call as predicate, right? So could have just done few things here. First of all, let's see what could be the basic intuition. At first, we are doing a previous, that is, we are considering on the list. I have told like we have n clothes lying around like this, and we have sorted them in this order. So first, to select this cloth, we need to imagine a distance this d greater than the d we have been given, just an imaginary distance. For that case, I have taken the previous as minus d, as d minus d will be always then always greater than equal to 0, the x dot first. That is, if even if the first floor starts at the distance 0, will always have an infinity to this side. So it nothing means more than that. So we increase the counter if we have got our whole array difference length here, and if we have got, then we increase the previous means to this point, right? So we increase the means, make our new previous this value. Then again check if this LD satisfies the value, then we again make our previous value this. So it goes on like this in general. And if the count is greater than k, we return true. Means that is normally return c greater than equal to 2. Or else, look how I have sorted here. It's sorted on the basis of last index here. So I told you this example 100, then 2, I guess it was 5, and then it was 6 and 9. So it had been sorted on the basis of the second value. So it sorts, it's a comparator function. So it takes in nothing and then assumes two value out of the array of V. And then we check if the first elements are same. Sorry, the second elements are same. This one, if they are same, then we return the ascending order of the first elements. That is AF is less than BF. Or else we return the ascending order of the second element. So what do I mean? If there would have had been a value like this, that there is 100, there's also 100 here, and then there was a value like 2. So what we would have done? So it would have simply returned, first it would have returned the value 2 comma 5. It's sorting on the basis of the last element, right? So it would have returned 2 comma 5, then 6 comma 9, then 1 comma 100, then 2 comma 100. So this would how the sorting would have looked like. Right? We can instead go in the way the normal sorting is done. That is, or else we could have sorted the same thing. If we would have done this, then we had nothing to do but to make a few different changes. If we had done sorting this way, then we had to make the predicate function a bit different, or what we would have done. So this is the previous counter. So I also told you, instead of, if we have sorted on the basis of last element, we should go in this direction. But if we have sorted on the basis of the first element, that is this one, we should go in the into this direction. So how does it look like? We have sorted on the basis of this element, right? So we need to see if this value, the front facing of this value, is greater than a infinity d distance from here. So we have just taken what can be the maximum value, 2e9 or something like that, whatever it was of the clothes length, and plus d. So plus d is, we can reach a 2e9 here, and d distance from here is kind of infinity for it. So we do a minus 1, and then we go on if the distance d is greater than this. So we hop on to this if this distance is greater than d, and if this distance is again greater than d, we hop on to this, and we increase our counter, right? We simply increase our counter. So we can do it in this way also. Instead, you can see the same code predicate 2's simplified version. So here what we do, we can always look, we can always select one cloth. It has nothing to do with the clothes remaining here or there, right? So our counter will always be at least one. and the previous value what it will have if we are going in this direction, what it will have a previous value of the first elements, means if we are going in this way or this way, it depends. If the first element's first value, if we have sorted normally, then it's the first value's first element, right? So it's the first value's first element we are checking and again increasing the counter. Then we don't have this boundary condition of taking the maximum infinity. People usually define the long max as maximum infinity. We can just say it as long max. It's simple. So instead of 2 now, we see the v of size as greater than 2, and we simply move on in this way and increase our counter. Now for the case of now for the case of binary search, how I'm doing binary search here. Look, why I have taken the highest value as 1e9 plus 5 in the question. It already mentions that we can reach till 10 to the power 9, right? It can reach 10 to the power 9. So what we see here, I have taken a value of 1e9 because the highest we can reach is 1e9 in general, but I've taken just 5 for a better, just in case thing. So h minus l is greater than 1. That is, we are always taking a bracket sequence of length greater than 1, h and l and h. Then for the mid, that is the middle element amongst them, we check if the predicate of, we have got our k, that is this c is greater than k, that k. Then we have got our mid. Mid is what? Mid is the distance d, probable distance d. Can it be possible? If it is possible, then yes. Then it's the probable distance d, and v is just a vector we are passing. So in this case, we increase our L2 mid or else decrease our H2 minus 1 because we want to not include the subspace which does not contain the false element. That's why we are making it minus 1. Or else if we wanted to include that, we should have just kept it just mid, right? But here we'll do minus 1 too. So now we check if the high count, that is this one. So what I had told you earlier, that how will our predicate value look like? Either it's binary search, after binary search, how will our H and L values look like? Maybe at L or H, this will be our means shortened up array, and then at H there can be a true, then at L there will be also a true. But we want to return the highest possible value, right? So we are just restricting us to the true search space. So at H, if there is a true, we simply see out H index. And if it's not the case, then there will be a for sure true at index L. And at H, we will have an F. So we'll index out, means we'll return the L's index. And if at none of them we have a true, we have false, thus, we have no true at all in the whole array. So we return simply a minus 1. So this is the basic question. And this is the answer of the question in this case. So we are just doing what? We are checking for all the possible distances in an increasing fashion. And then we see if we have got our value, that is possible value for the values remaining or lying in that range. Then we just see out that index, or else we see out minus 1, right? So making the, so the time complexity is n log n, log n for the binary search part, and n is for the means for calling we are doing for each function, right? We are not calling each function, it's mostly log of n only, I guess. So yeah, this is what we are doing in general. You can get the idea. Also, the main Thing was that the interview interval scheduling thing, we could have done it in O of n square, but reducing it to O of n was the hint we were getting. So we cannot do it in n squared log n. So we had to, it had to be done in n log n, right? So this was the question, and this was the solution. If anyone has any doubt, they can ask me. Okay, so we'll end the PCD now. Thank you.
अच्छा, तो रिकॉर्डिंग बंद कर दिया ना? हाँ, रिकॉर्डिंग कौन कर रहे थे?
भैया अनिंदिता कर रही थी।
ओके, ठीक है। तो बताओ सब, कैसे वैकेशन चल रहे हैं सबका?
ठीक, बेकार जा रहा है भैया, पूरा दिन सो रहे हैं बस।
अरे थोड़ा
अच्छा है भाई।
मतलब सोए तो ठीक है, मतलब कुछ-कुछ बस पढ़ाई करते रहना बस, मतलब